All right, so the next homework assignment is due after spring break, right? April 10th. So you've got some time ahead of you. I hope that you have something fun planned for spring break besides homework and studying and getting ready for midterms. At least one day on the beach, something like that. All right? That's your assignment from me. Spend at least one day doing something fun. But your real assignment is homework 4C. All right? The graded assignment is homework 4C. The ungraded assignment is enjoy a nice spring break. All right, today we're going to be talking about Bernoulli's equation. So, any questions before we get started on that? All right, let's go through the background and try and remember where we're at. So far we've discussed Euler's equation, which was the application of local acceleration. And so in Euler's equation we are looking at how velocity changed over time. And what Euler's equation told us is that some acceleration, over here on the right side, some acceleration in the L direction meant that the pressure would be different between 2 points. Or the elevation would be different between 2 points. Or possibly both, if the container was open to the atmosphere. And so here inside of the brackets here is the piezometric pressure. And so it says that the sum of the pressure plus gamma z changes in response to this local acceleration. Bernoulli's equation is applying the principles of convective acceleration and looking at how elevation and pressure are affected by convective acceleration. Now, what we're going to look at today is how the velocity changes over position and specifically how that changes the pressure. So here is Bernoulli's equation. And there are some important assumptions that go into Bernoulli's equation that we're going to talk about today. But what it's saying is that if you pick out 2 points, then there is a constancy in the pressure head. So P1 divided by gamma, this term we're calling the pressure head. And the reason why it has that name is that the units, instead of units of pressure, which normally we'd describe in pascals or newtons per meter squared, when we have the pressure divided by the unit weight of the liquid that we're talking about, then this has units of meters. And so you'll notice we're going to be adding it to an elevation term. So Z1 also has units of meters. And they all have the same units if we can add them up. So this first term is called the pressure head. The second term is the elevation head. And the third term, V1 squared divided by 2g, that's called the velocity head. And one way of thinking about these 3 terms is that together they account for all of the energy in the system at a single point. The first 2 terms can be thought of as potential energy. The second term can be thought of as kinetic energy. And so between 2 points, there's no loss in the energy. Now later on when we get to chapter 7, we're going to start looking at empirical ways of accounting for frictional losses between 2 points. But here in Bernoulli's equation, what we're going to do is apply this equation in circumstances where hopefully the energy losses are relatively low, so that then this equation is pretty accurate if there's relatively small energy losses between 2 points. Now, there's a series of assumptions and application limitations we have from Bernoulli's equation. And understanding this bullet point may be the basis of some future concept question that you could be asked, like in a quiz or final exam or something. So let's spend a moment to talk about this. The Bernoulli's equation comes from applying Euler's equation. We've already talked about that. So Bernoulli's equation is about the application of convective acceleration to steady flow along a streamline for an incompressible inviscid fluid. So let's see how many different assumptions there are there. So steady flow is the first assumption. So it says for Bernoulli's equation to be accurate, for you to be like having a physical system and using this to predict what's actually going to happen with the pressures, the first thing is that your flow should be steady. So what does steady flow mean? No change over time. So it means that if the flow rate right now is 5 liters per second, then the flow rate in 10 minutes is the same, and in between it's staying constant. Okay, so the first assumption is for Bernoulli's equation to be accurate, we should have steady flow along a streamline. Now what we mean by that, along a streamline, here let me draw a nozzle. It's an expansion, and we have water that's flowing this way. Here's our streamline. But here's another streamline that's sort of curving outwards a bit, and another streamline. It's showing the direction that the flow is going. It's sort of like a velocity vector that gives you an idea of the direction of flow. So along a streamline means that you can't accurately apply Bernoulli's equation and use this as location 1 and then as this as location 2, because they're on different streamlines. And so one of the best ways that we can make sure that we're doing it the right way is just use Bernoulli's equation at the center of a pipe, because then that's on the same streamline. And it's easy to measure the elevation of the center line of the pipe, because if there's an expansion, then the elevation isn't changing. And so it also has sort of a simplifying effect in some of the problems that we solve. But that's what we mean by along a streamline. If you draw an imaginary line that depicts the velocity of the flow, that's the streamline, and you're supposed to apply Bernoulli's equation between 2 points that's on the same streamline. So any questions so far? Steady flow along a streamline. For an incompressible fluid, so name a fluid that's relatively incompressible. Mercury, okay, true. Mercury is relatively incompressible. Water, the most common liquid that we have. So fluids include gases and liquids. So the term fluid means gases and liquids. And so liquids are relatively incompressible. So what's a gas that fails the incompressibility test? Air, nitrogen, helium, gases. And so what this is saying is Bernoulli's equation is pretty good as far as the incompressibility assumption goes. It's pretty good for water, not so good for gases, because gases are compressible. But now look at the next assumption, inviscid. Now you may not know what that term means, but you know what it goes along with. It means viscosity. So an inviscid fluid is a fluid that has no viscosity. Well, that fluid doesn't exist. There's no fluid that has no viscosity. All fluids have some. Liquids have a pretty high viscosity compared to gases. Gases have a very low viscosity. So gases are good at satisfying the inviscid assumption. They were bad at satisfying incompressible, but gases are good at satisfying inviscid. So here we have a series of assumptions actually that can never be strictly true. That's one of the weaknesses of Bernoulli's equation, is that it's this theoretical equation that actually is never going to be true, because we're saying between 2 points there's no energy loss, and there's always going to be some energy loss when water flows between 2 points. Even if the 2 points are close together, like they are here in this drawing, even if they're just half a meter apart, as the water flows from one point to another, the pipe is going to be resisting flow. And as the pipe resists the flow, there's some fluid drag, and that's reducing the pressure in the direction of flow because of the energy loss. So Bernoulli's equation, there are some circumstances where it does a pretty good job, and then there's some circumstances where if you're trying to use Bernoulli's equation, you're going to have a huge error. For example, if two sections, if point 1 and point 2 are very far apart, then you're going to get a lot of error trying to model what's happening with Bernoulli's equation, because there will be a lot of energy loss, because the inviscid assumption is not valid, and the further apart 2 points are, the more we're going to feel it that we're not honoring the inviscid requirement. Incompressible. And so if you have gases flowing through a section like this, the pressure is going to change partly because of changes in velocity, but the pressure can also change as the gas expands and contracts. And so this isn't something I want you to stress too much about, but when you're in the lab doing physical experiments to test Bernoulli's equation, sometimes you'll see that it doesn't give you a perfect answer. And most times when you have a difference between what you predict with the equation and what you measure in the lab, the difference is because somewhere along the line our assumptions aren't exactly right. So this is a very useful equation, but it has its limitations. Any questions about that? All right, so keep those limitations in mind. Let's talk about a model. A model, maybe you built models when you were younger, like little model planes or model cars. If you've walked through the mall, you see models sometimes of buildings where they're trying to sell real estate, get someone excited about purchasing a new ocean view apartment. So a model is a conceptual, mathematical, or physical representation of a system. It's a way of simplifying reality and trying to show this is what reality is going to look like, or this is how reality behaves. And here's a picture of a clay model of an aircraft. This is a Boeing 747, and it's in a wind tunnel. And models are useful for making small changes in a place where it's easy to make a small change. It's very easy to change a clay model in a wind tunnel and then test to see how did that change affect conditions. It's easier than taking a full-size Boeing 747 and making a change with that, because that would be dangerous and expensive and maybe time-consuming. And so a model is useful because it allows us to predict what's going to happen in reality. And this is a model. This equation is a model of predicting what's going to happen in the world. And that's why equations are useful to us, is they allow us to do design or analysis and estimate reality without having to do trial and error with the physical system, because that can be dangerous and costly and time-consuming. So models save us a lot of time. Here's another model. Now there's something different between the one on the top and the one on the bottom. The one on the top is a fundamental model. This is a fundamental equation that's built from the ground principles of physics. Whereas the second model, range equals fuel divided by some factor minus another factor times weight and so on, this is an empirical model. And the empirical model is built not by analyzing the laws of physics, and it's not built by doing a derivation. An empirical model like this is usually built just by looking at what has happened in the past. Looks like this model is trying to predict the range. And one of the variables that we're putting in there is fuel. Another one is weight. But you would just have a bunch of data, and then you'd try and make the best equation that fits the data. And so an empirical equation is one that's constructed based on the available data without really any strict connection to the fundamentals of physics. All right, so there's the full-scale prototype and the small-scale model. One of our last class periods is going to be talking about some things from Chapter 8, which comes back to the idea of models and prototypes, and how is it that such a small model like this can be accurately scaled up to a full-size prototype. It's a pretty interesting subject that we'll get to in Chapter 8. But what I want you to remember now is that in engineering models, there are boundaries that models are applied to, the limits in which they're valid, the variables that go into models, and then the parameters. So parameters are elements that don't change, like the density of a fluid, whether it's air or liquid, the viscosity, gravitational constant. But some of the variables we're going to be changing as water flows through a section like this, for example. The velocity, the pressure, the elevation of the liquid is going to be changing. And then the boundary is the system itself, like the pipe or the nozzle that the water or the gas is flowing through. So models are useful. And back to the idea of the Bernoulli equation, the assumption, steady flow, incompressible fluid with no viscosity along a streamline, what that tells us is that the sum of these two terms, the piezometric pressure and the kinetic pressure, are equal. Now let me show you the other way that we were looking at Bernoulli's equation just a moment ago had units of meters. So we had the pressure head, elevation head, and velocity head was constant. So this is just saying another way we can measure it is in terms of pressure plus gamma z plus the density velocity squared divided by 2. And that's constant. So the only difference here is that if we divide each term by gamma, so then we'd have pressure divided by gamma, Z1 for this term. If we have the density divided by gamma, remember that gamma is density times G. And so this is saying if we have the density and divide it by gamma, then that leaves us with a G in the denominator. So there's a constancy as the flow goes along the streamline in those things. So either form of these equations can be used to solve problems. Most of the time, though, I tend to solve them in these terms. And as you move into 341 in the fall, are all of you registered for, oh, you haven't done registration for the fall yet, have you? Okay. I assume that each of you are going to move on to 341. It's best not to delay that course. You're going to use this form of the equation a lot in hydraulic design. So here's an instance. We've seen something like this before. Remember when we were talking about acceleration as a function of position, we said that water was flowing into a valve, and because of the shape of the nozzle, it's forcing the flow through a smaller cross-sectional area, and so the velocity increases. What we could do is we could use this equation to tell us how does that change affect the pressure. So before we do any calculations, just look at qualitatively at the equation here. Let's look at Bernoulli's equation, and we see that the flow is going from 10 meters per second to 20 meters per second. So is the pressure going to increase or decrease if we are to apply Bernoulli's equation along a streamline? So along a streamline, the best way to honor that is to just do it at the center line of the pipe. So if this is our location 1, where the velocity is 10 meters per second, and here is our location 2, what's going to happen to the pressure as the water goes through that valve? Because we're going to see the velocity here, this one is 10, and this one is 20. The Z1 and the Z2 are equal. Okay, so if this goes up, then P2 is going to have to go down for the 2 to remain constant. And so we see that the pressure is actually decreasing for this one as the water flows from the left to the right. So that's a little bit counterintuitive, I've found. In the past, sometimes students wonder, if the water is getting squeezed into a smaller area, why is the pressure decreasing? And, I guess conceptually I can see how that maybe would make sense, that you think that the water has less room, so wouldn't the pressure go up? But no. What we know is Bernoulli's equation says that the sum of the energy, if we're ignoring energy losses due to pipe friction, the sum of the energy has to be the same. And so if the velocity goes up, that energy for the velocity to go up has to come from somewhere. You can't just have velocity increase without the energy coming from somewhere, and that somewhere it comes from is from the pressure head that was existing at location 1. So let's try that out. This one was a contraction. This was a pipe contraction. This is a pipe expansion. And what I'd like you to do is consider, here at location 1 we have 5.5 meters per second. Here at location 2 we've got 0.6358 meters per second, and we know the pressure at 1. That's given, 400 kPa. I'd like you to see if you can find the pressure at 2. Now, based on what we just saw, would you expect the pressure at 2 to be higher or lower than the pressure at 1? All right, let's see if that's true. All right? All right, as I was walking around, it seemed like almost everyone I checked had this correct answer, 415 kilopascals. Good. the velocity that was at 1, we had the velocity decreasing. So the way you can think of it is you had some energy tied up here in the velocity head. So where did that energy go? The energy can't just vanish without a trace. It has to go into something. So if we're talking about the center line of the pipe, the elevation didn't change. The water is still flowing from center line to center line. So the extra energy that was in the velocity head got transferred into additional energy in the pressure head. So that's why the pressure went from 400 kPa to 415 kPa. All right, now I know that I've given you the advice so many times, always write your units as you're doing these because it will eventually catch a mistake that would be otherwise very costly for you. The other advice I want to remind you is sometimes it's valuable to write as many steps as you can. Instead of trying to save pencil and save paper, write as many steps as you can because that is another way of making sure that you have fewer mistakes. You can see each of the 3 terms and then what those break down to in terms of the pressure head, the velocity head at 1, velocity head at 2. Now this one's probably possible to do the calculations in the calculator without writing anything down, but then if you do that, what do you have as a reference as you're working on the homework this weekend, over spring break maybe? So making as many notes as possible can be a useful thing. All right, so let's take this up a notch. Let's complicate things. This definitely looks complicated, but this is 2 simple ideas, putting 2 things together. So here we have a manometer underneath the nozzle, and then the nozzle, just looking at it, with air flowing through there, tells us we have a Bernoulli's equation. So we're going to use both the manometer equation and Bernoulli's equation. And here's what we know, is because of the shape of the nozzle, the cross-sectional area at 1 is double the cross-sectional area at 2. And so what that means is that the velocity here, after it's contracted, the air velocity is double the air velocity that there was at 1. Now we don't actually yet know what is the velocity, but this manometer equation tells us that the pressure inside the tube here is greater than the pressure there. A funny thing is happening. As the air is flowing through, it has a slow velocity at first, and then the velocity is speeding up because of the nozzle. But then when the air goes into this tube, it stops. It's called a stagnation point. It's like a dead end. The streamline is going along and then it stops instantly. And so all of the velocity head that was in the air, once it bumps into this tube, it's transferred into additional pressure. Now there's plenty of air that's going around the tube. So not all of the air stops. Some of it's going underneath this manometer opening. Some of it's going over the manometer opening. But the streamline that's at the center line here just stops. And so all of the energy that was existing as velocity head is turned into extra pressure head. And the reason why that's useful is that this deflection, this 10 centimeters of water, what does it represent? It represents the difference in pressure between here and there at the opening. And so let me give you a small hint before I give you some time to start working on this one and thinking it through. The first thing I'll tell you is that we apply Bernoulli's equation through a fluid, whether it's a gas or a liquid, but point 1 and point 2, we should be going through the liquid. So those 2 points, you can't go partly through air and partly through water. And so in this problem, we're going to assume that 1 and 2 are at the center line, and then we're also going to consider the conditions immediately inside the tube. And so let me tell you what I mean by that. Here's the nozzle. It's contracting down. So here's location 1, and it's along the streamline. Here's location 2, and then here is the opening of that tube. And I'm going to say, let's say this is location T. It just means in the tube. So there's a constancy in energy between 1 and 2, it looks like since the velocity is going up, the pressure will decrease between 1 and 2. And then between 2 and t, there's still a constancy in energy. But the form of the energy changes a lot. Because here at 2, we've got a lot of velocity, and at t, there's no velocity. The elevations are the same, so all of the velocity head that there was at 2 gets changed into additional pressure at t. That's what's happening there. And then how much additional pressure? Well, we can measure the pressure difference using the manometer equation. And the manometer equation is going to relate the pressure at 1 and the pressure at t. So the change in pressure is going to be a function of the delta H, the deflection in the water that we see there, and the gamma. Now this is where a problem like this can get a little bit potentially confusing because we've got two different fluids. So when we're talking about Bernoulli's equation, this is air that's going through the nozzle. And so we know about the air, the density is 1.2 kilograms per cubic meter. And then inside the manometer, where we're using the manometer equation, that fluid is water. And so the gamma for that is 9810 newtons per meter cubed. So when you're using Bernoulli's equation, in this problem, we're talking about air. When you're using the manometer equation, in this problem, we're talking about water. All right, so one last hint. What we're saying basically is that the pressure head divided by gamma plus Z1 plus V1 squared divided by 2G is equal to the pressure head at 2 plus the elevation at 2 plus V2 squared divided by 2G. And it's also equal to the pressure at location T divided by gamma, Z sub T plus Vt squared divided by 2G. So really what we're going to do, we're most interested in the relationship between 1 and T, because that's what we're going to measure with the manometer equation, is the change in pressure between 1 and T. That's right. The velocity of the air inside this tube is 0, because this manometer, remember we were doing manometers way back during the hydrostatic chapters. And so the fluid is not flowing through this manometer. So once the air gets into this tube, the conditions are static. So V sub T is 0. All right, so start taking a crack at this. Let's see if we can make any sense of what is the velocity at 2. And what we're looking for is a measurement in terms of meters per second. And we have enough data to tell us how many meters per second the air is going at location 2 before it hits that stagnation point. All right, so it's pretty obvious that if we're taking point 1, 2, and 3 on the same elevation plane, since all of the z's are equal, then we can just leave them out of the equation. And we already have said that this is a stagnation tube, and so the velocity inside the tube is 0. And so Bernoulli's equation simplifies down to the pressure head at 1, the velocity head at 1, and then the pressure head at t. So that's ultimately what we're going to substitute back into once we solve the manometer equation. And so the manometer equation is telling us the change in pressure between T and 1 is 981 newtons per meter squared. So that's the difference in pressure. Now we don't know the absolute pressure at either of them, but we just know that's how much the pressure change is. And so then we can substitute that pressure change into Bernoulli equation. So here's Bernoulli equation from above. I've just sort of multiplied each term here by gamma to simplify because I'm going to have P1 versus PT over here on the left side of the equation. And then rearranging to solve for the unknown, V1 is what we're going for. Let me make that a little bit bigger. So, you know, the algebraic steps you go through may be different from this, but in the end, what you're looking for is you need to remember to substitute in here the density, or depending on what form you're solving, the gamma of air. And so the density of air is 1.2 kilograms per cubic meter. If you did it in terms of the gamma, it should be 11.77 newtons per cubic meter is the unit weight of air. So 40.4 meters per second. How many people got that? A lot of people. Good. All right. So Bernoulli's equation is very useful, but remember, when we're talking about fundamental equations, they have respectable, lofty origins, but they also come with limitations. And so the limitations for Bernoulli's equation, what we're assuming is that we're applying it for steady flow, meaning the conditions are constant over time, along a streamline for an incompressible, inviscid fluid. So either a fluid is going to be relatively incompressible, meaning that it's probably a liquid, or it's going to have a very low viscosity, meaning that it's a gas. But it's not going to satisfy both of those. And so there's no perfect fluid for which Bernoulli's equation describes things exactly. But if we apply Bernoulli's equation in a smart way, then it can give us very useful results. All right, that's all I have for you today. Remember that you could get an early start on the homework and then save yourself the worry and concern for doing it later. I'll see you on Tuesday.